with? Okay, there we go. Hi, this is Mrs. Sloan, and this is our 7th period review for Honors Bio, and this is all things energy and enzymes. So I'm going to record this now. Hopefully, I'll be able to get that out to you in case you missed this review or you want to watch it again because it's so interesting. Okay, let me make myself a little bit smaller. Okay, it's weird. Hang on. Will it work? Hang on, be patient. Be patient. Go. It's probably freaking out. Okay, there I am. Good. Okay, and then we can make this go away. Here. Okay, so I'm going to go ahead and start. This Pear Deck code will not work for you at this point because this was a live Pear Deck code. So YZNHUA. So I'm going to go ahead and start. All right. Great. I'm so glad it went 3 steps. So, bye, Nikki. So the first thing on the slide is to show you what I want to make sure that you understand the different expectations for this. I'll get back to it. Sorry, everything is slow because I'm trying to record it. The computer cannot handle everything. All right, so can you answer the following questions? For chapter 6, what are the 2 laws of thermodynamics and how do they apply to cells? And then relate that to entropy and free energy. So highlight the things you think you need to work on or make sure I address today. Compare and contrast anabolism versus catabolism, reactants versus products, exergonic versus endergonic, exergonic versus endergonic reactions, competitive versus non-competitive inhibitors, and oxidation versus reduction, cellular respiration versus photosynthesis. So I know that's a lot of compare and contrast, but I just want to make sure you can keep them all straight. And then make sure you understand what a coupled reaction is and the use of ATP, and what do enzymes do, what don't they do, and what factors affect enzyme activity, and then don't forget to do your additional objectives. So take just a minute and tell the person next to you which of these items listed here are your biggest concerns that you want to make sure I review today. Go ahead, have that discussion. Go ahead. Which song? There's cellular respiration and photosynthesis. Oh, the thermodynamics one, maybe? Oh, no, that isn't until the next chapter, which we start talking about tomorrow. Yeah. Okay. Come back to me. Do you know what you need to focus on? So you're going to maximize our time together today? All right, I'm going to keep going then. The first thing we want to review are the laws of thermodynamics. So let's review that together. Do you remember I made up something on the spot? Let's see if we can remember it. The laws of thermodynamics, the first law says that energy is not created or destroyed. It just changes forms. And every time it changes forms, the second law says you lose some as heat. Okay, you got those 2 down? So here we can see ultimately our energy comes from the big yellow one is the sun, right? And then that energy, do we capture every single ray of light by plants? Do autotrophs capture it all? No. And then of the light that the plants capture, right, they're converting that light energy into the chemical energy of sugar. What process is that called when you convert light energy into the chemical energy of sugar by reducing CO2 into glucose? What do you call that process? Photosynthesis. Does all of it get transferred? No. What law says not all of it gets transferred? Second law. Good. Okay. And so are you comfortable with those 2? All right. Then the next thing we talked about is the idea of entropy overall. And that entropy is that we go to greater and greater what? Disorder, right? Disorganization. So if you give somebody, if 10 is a lot on your scale and 0 is nothing, when you talk about giving somebody a 10 relating to entropy, are you saying they're highly organized or highly disorganized? Disorganized. And we're always fighting that disorganization. And that's why we need to breathe and eat food so we can make ATP to fight that disorganization. Yes? Okay. And once we get something organized, we can use it like a charged battery in order to do work. right? And we talked about free energy was the energy available to do work. Yes. And when we talk about something like glucose versus carbon dioxide and water, we know that glucose, we think of it like a Lego, has all those connections, and all those bonds are sharing what? What are they sharing in those bonds? When you share in pairs, what are you sharing? Pairs of electrons, right? And electrons are energy. So the more complex the molecule is here, then the more energy you have that. But as you break it down, entropy increases, right? Disorganization, we go from more energy, free energy, energy available to do work, to less energy available to do work. Yes? Okay. And when that transfer takes place, you can harvest some of that energy to make what? How do we store energy in our cells? How do we use, what kind of energy form do we use in our cells? We use ATP. Okay, and that's interesting that I can't write on that. Or maybe it'll do it as a delay when I'm doing it. Oh, look, there it is. And is that 100% efficient? No. It's best if we have oxygen, right? It's best if we have oxygen, at least we get to like 39%. Without oxygen, only 2%. We're going to be learning about that. But we transfer it. So this right here, the carbon dioxide and water, entropy is high, right? What happens to our potential energy? As entropy goes up, what happens to our potential energy? It goes down. Exactly. So when we look at the second scenario over here, okay, when we look at concentrating hydrogen ions to one side of a membrane, we can harvest that. It's like water behind a dam, because we know that water wants to get to the other side of the dam because entropy is always increasing. So the channel we make is actually a protein that is what? Enzymatic, and it's like a turnstile. Everybody wanting to go into Disneyland when it first opens, when you go through that turnstile and you turn it, you can snap a phosphate onto ADP, making what? ATP, the energy currency of the cell. And so this right here is low entropy, but it has a lot of potential because we can harvest it. Once the hydrogen ions get to the other side, our entropy increases and our potential decreases. Turn to the person sitting next to you and say, are you good? Are you good? Do you need any help with that? 1 second. Hang on 1 second. Okay, come back to me and ask me your questions. I'll tell you no lies.
Is ATP reusable? Like when you break it, you release the energy, you get ATP.
Yeah, if you break a phosphate off and make ADP plus a phosphate plus 7.3 kilocalories of energy, you can then use that ADP to reform ATP. It's kind of like if you have a Lego, right, and you break it, can you rebuild your Lego? Yes. Yeah. If you have all the parts, you can rebuild the Lego. Will it require energy on your part to rebuild that Lego? Yes. An input of energy. Yes.
Was there a certain amount of energy that you use every time?
You don't have to memorize it. I know what it is, but 7.3 kilocalories, but you don't have to memorize that. Yeah. Okay. Anything else on this page? Feeling confident? Okay. All right. So then the next one I have here, where are you? Is metabolism. So your metabolism is all the enzyme mediated reactions in our body. And now we know what enzymes do, right? Those are organic catalysts and they do something for us. What do organic catalysts do? Or any catalyst, they will lower the what? Energy of activation. Remember how we talked about all reactions require the input of energy, but you would think, remember when we talked about exergonic versus endergonic, right? Exergonic, release, endergonic, takes in, right? And in exergonic reactions, even though you're going to greater disorganization and you would think it would be spontaneous, which it is, there is still that hurdle that you have to get over that kind of maintains the integrity of that system. And lowering that hurdle is what enzymes will do to make that one reactions go forward. Remember, if I compare it with heat will make any reaction go forward because you increase the kinetic energy, right? So it's more likely to occur. But we want only specific reactions to go forward, and that's why we use enzymes. So here, when I say enzyme-mediated reactions, I mean an enzyme is involved in this reaction. Okay, and there are two types, anabolic and catabolic. And anabolic are those that build, right? Maybe you're building a protein, building muscle, building a hormone in your body. building a protein. Did I already say that? And then catabolic reactions are about breaking things down. Okay. Ask your bio buddy. You good on that one? Anything you need? Got the difference between those two? All right. So then next thing I want to review is reactants versus products. And you just want to remember that reactants are what? What? Yep, so it's what you start with, whereas products are what you end up with. And whenever we studied reactions, we compared reactants and products energy level, right? So without showing it to you, I'm trying to see what you remember. So if I say I have an endergonic reaction, I'm putting energy in, so my products will have more free energy. Exergonic, my reactants have more energy, right? Because I release that energy out. Okay, so that's why I want you to remember reactants and products. The other reason I want you to remember it is we talked about specifically photosynthesis and cellular respiration later in the talk, where we said, okay, the products of cellular respiration are actually the reactants of photosynthesis and vice versa. Do you remember that part? So that's another thing you would want to remember. So how do we measure free energy? Well, we look at the changes in free energy, and that triangle right there stands for delta. So that's a change in the free energy. And if my products, remember when we talked about negative and positive delta G, see if the person next to you remembers the difference between negative and positive delta G and what kind of reaction that is. See if you can remember. Go ahead. If your bank account goes down, have you gained money or lost money? Lost money. So if your delta G is negative, if it goes down, you have lost energy, right? If your bank account goes up, you have a positive delta G, you have gained energy. Where do we see that? Endergonic reactions, the products have more free energy in endergonic reactions right here. When you look at your initial energy to your final energy, the products have more energy than the reactants. That is a positive delta G. That is an endergonic reaction. The opposite of that, if I have a negative number on my bank account, I know I have lost money, right? The delta G is a negative value. And you want to remember, like on a quiz or a test, what I would probably do is the hurdle right here, I'd want you to know is the energy of activation. And I think you can remember that graphic that I had when I was first presenting this, but this right here is the delta G. Delta G, you just look at the difference of final minus initial. You don't look at the energy of activation. Now, what do I know will lower this energy? So slow. There it is. What do I know will lower that energy of activation right there? An enzyme, right? An enzyme will make this reaction more likely to occur. Okay, and then I just, I can erase that. So these dots mean something. Can you figure out what these dots mean? So if it's an exergonic reaction, right? My products have less energy. See what I was trying to show you there? Products have less energy in the reactant, and the reactants have more, and it requires an input, got bigger of energy in this one. Products have more free energy. Okay, check with the person next to you. Are you good on exergonic, endergonic? Do you have any other questions? Anything you want to talk about with that? All right. So then next I want to talk to you about ATP and remind you what that is. So ATP stands for adenosine triphosphate. And remember, of the 4 important organic molecules, what is ATP? Yes, nucleic acid, right? Remember nucleic acids? Yes. Nucleic acids are built out of nucleotides, and nucleotides have what 3 things? Phosphate group, nitrogenous base, and a sugar. So we're going to find those 3 things in ATP because it has a nitrogenous base whose name is adenine. It has a sugar whose name is ribose. And then it has a phosphate group. Oh, bonus phosphate. Oh, bonus phosphate. And that is that high energy bond between that second and that third phosphate. Okay, so when we look right here, we can see we're snapping off, this is our before, right? And we're snapping off one of those phosphates. What's this water right here for? Hydrolysis. So we're breaking off that phosphate. And when we do, some energy escapes, right? Because that was a shared pair of electrons right there, and we release that energy. So we get energy. Then we have the leftover ADP and the leftover phosphate that we just broke off. Now, if it releases energy to go in this direction, we must have to put energy in to go back to reform the ATP. Yes? Does that make sense? Okay, check with the person next to you. See if you are confident. And we're good with that. Things you want to ask me? Are you all good? Okay. So then why do we even need ATP? And that's right here. So chemical work, like if you're going to synthesize something, active transport, we know all about active transport, right? And then if you're going to do mechanical work, like sliding filament theory, like muscles contracting, those are the three biggies that you need ATP for. So you couple, remember coupled reactions. If one reaction is exergonic, right, like two ships that pass in the night, if one reaction is exergonic, it can give that energy to a ship going the other direction that's endergonic, right? And so we see that here in this picture, if it shows up. All right. So here I will spin my ATP when I'm doing anabolic reactions. What are anabolic reactions? Building or breaking? Building. Anabolic is building. It costs me energy. Who's going to pay that energy bill? ATP, right? And so I can synthesize things, complex polymers, I can synthesize. Now, if I break those complex polymers up, they will release energy, and I will couple that with the rebuilding of ATP. It's a circle of life symbol, right? So you want to have enough ATP to build what you need, and then when you break things down, you can harvest that energy to build other things you might need. Okay? Ask your bio buddy, are you okay? Questions you want to ask me, I want you to feel confident. Okay, so then we next transition to talk about enzymes. And there are a couple key things about enzymes we need to know. Enzymes are built primarily out of what? What are most enzymes made out of? Proteins, exactly. And we learned, when we learned the 4 important organic molecules about primary, secondary, tertiary, quaternary structure, yes, to build our proteins. So they're going to be susceptible to anything in the environment that would change that shape that they have. What are some things that could change an enzyme shape in the environment? If you alter what? Temperature, right? Just like we cook eggs, that's a protein. It changes the way it appears. Temperature, what else? pH could change it. What else could change it? Could something binding to it change it? Yeah. And what's the special part on the enzyme that's critical to its functionality? What do you call that special place? The active site. And what happens on the active site that's so important? It's where the substrate binds. If the substrate can't bind there, then the enzyme can't do its job. That's not necessarily a bad thing, because sometimes we don't want an enzyme to do its job. We have enough of whatever it would build or break down, and so we don't want it to do anymore. So we can use that in a regulatory fashion, right? But the active site is where it binds to that substrate. Are enzymes specific? Yes, just like all proteins. And we learned about channels, carriers, cell recognition. Proteins, by their very definition, are specific. And so are enzymes, and that's why they're oftentimes named after whatever their substrate is. Now, when they're totally dialed in, when the active site is filled with that substrate, we call it an enzyme substrate complex. And sometimes when it's binding, it can actually change its shape temporarily, and we call that the induced fit hypothesis. Will this enzyme recover to work again? Yes. Did it work again when you did your liver lab? Yeah, you poured off your product, right? And then you added more hydrogen peroxide, and did it bubble all over again? Yeah, because the catalase was not destroyed by that reaction. It could be used, and if you had poured it off again and added more hydrogen peroxide, it would have continued to bubble. Okay? Questions you want to ask me about that? We'll check with your neighbor first, because you might be more likely to be honest with your neighbor before me. Ask them, are you okay? Anything you don't get? All right. So what do enzymes do? They take something that may or may not happen spontaneously, and they make it more likely to occur by like 10,000 to 100,000 times more likely statistically to occur. And they do that by lowering the energy of activation. With that lowered hurdle, kinetic energy itself is enough to make that reaction occur. The pathway towards entropy is enough to make that reaction occur. And they're very specific to their substrate, and in fact are named after it. And here you can see the delta G is still the delta G. That never changes. Enzymes do not affect delta G. They don't affect your starting energy or your final energy. The only thing they affect is that hurdle to get that party started. They make it more likely to occur. Okay, we good on that part? Okay, then I just did a massive slide of all things, like a little summary slide of all things that could affect energy and enzymes functionality. So let's go through all of them so we feel comfortable with it, okay? So in the top left-hand corner, if you increase the substrate, you will increase the productivity, right? Up to a point until all the active sites are full, right? So that's one thing. We would get more and more product if you added more and more hydrogen peroxide. This one is all about what? What's that special number right there? pH, right? We know the enzymes work at a specific pH. Why? Because the amount of hydrogens, what kind of bonds do we sometimes make with hydrogens? They're called bonds. Hydrogen bonds, right? So that can influence that enzyme, its shape, because you can denature it or change its shape or make it active depending on the pH of its environment. Like in your stomach, the enzyme you need to make your stomach, the pepsin work, has to be a very what? Low pH, right? All right, what's another thing that can affect it? Can I move myself? Oh, I am moving myself. Oh, okay. So here we can see competitive and non-competitive inhibitors. Competitive inhibitors bind to the active site, so they're competing with the substrate, right? Whereas non-competitive inhibitors bind to a secondary site, an allosteric site, which ultimately changes the active site, right, in an indirect fashion. So I wanted you to remember allosteric site. What's this word right here? Temperature. Good. And this one over here, we had cofactors and coenzymes, which sound very, very similar. Coenzymes, the key thing there was just that they're organic, whereas cofactors are inorganic, like metal, like in hemoglobin. Iron has to anchor our red blood cells. And I'm sorry, I guess I didn't make this a draw slide, did I? Are you going to live? Are you okay? All right. And then here we looked at feedback inhibition, which is there's a series of reactions all requiring their own enzyme. So you could have A going to B, B going to C, C going to D, D going to E, and all of those have a different enzyme that catalyzes it. And whatever the end product is, in this case it was F, whatever that end product is, can go back in end product inhibition, and it can bind to the enzyme and change its active site and inhibit it from going anymore, which is fine because we have all the product we need. And when that product level decreases, just like you set your oven, I always use the cooking example. I set it to 375 in order to cook my cookies. Once that oven hits 375, I want my oven to shut off, right? Because I don't want it to get any hotter and burn the cookies, right? So as long as it's hot enough, it shuts off the oven, but if the oven gets too cool, it'll turn back on. So that's what you're doing in order to regulate what reactions take place when. Okay with that? All right, moving on. Then we talked about the idea of being reduced and oxidized. Hi. Oh, I know. Let's see if we can get it right here. So a couple things we want to remember on this, okay? When we talk about getting reduced, okay? Reduced, okay? Reduced means you have more energy. Okay. But the confusing part is that I'm saying reduced, yet I have more energy. And the reason why you use reduced is because what do I have more of that would reduce my charge? I have more what? Electrons. And electrons equal energy. Okay. Electrons equal energy. So the more electrons I have, the more negative charges I have, so I become reduced. Now, how can I get more of those electrons? Well, my helper friend, who's my helper friend that I really like a lot? Hydrogen. If I hook up with hydrogen, will hydrogen give me their extra electron? Sure. So I can hook up with hydrogen to get reduced, or I can gain electrons, or I can gain energy, or who should I break up with if I want to have more energy? Oxygen, because oxygen is my taker friend, right? So if I can just get rid of oxygen out of my life, right? It's like the hole that all my energy goes into, right? If I can get rid of oxygen, then I will have more energy by getting it out of my life, right? The opposite of that is being oxidized. Right off the bat, you'll be able to remember because it says oxidized, you must be gaining what? Oxygen. You must be losing your good friend hydrogen, or you're losing energy, or you're losing electrons. Why do we talk about that? Because we have to go back to the first law of thermodynamics, which says what? Energy cannot be created or destroyed. It just what? Changes forms. So how can we have it change form? You just pass the electrons to the next compound, and you're passing that energy along, right? That's how we do that, through a series of reductions and oxidations. And because they happen simultaneously, you call it a redox reaction. Because when one thing's getting reduced, it can't happen in a vacuum. If it's getting reduced, something else must be getting what? Oxidized. And then the example we used in class is the electron transport chain, which must be transporting electrons, right? And remember how I had you pass pins along? And we talked about redox reactions, which in mitochondria and chloroplasts, you harvest that energy through the passing of energy. You harvest that to put hydrogen ions to one side of a membrane so you can make some what? ATP. Good. And then we looked at, can I go off this slide? Or yes? Lose electrons. You are welcome. Anything else before I change this one? Okay. So then we compared and contrasted photosynthesis with cellular respiration, which the next two chapters, your next chapter is cellular respiration, then the chapter after that is photosynthesis. So it'll, make a little bit more sense to you once we've gone through that. But what I wanted you to see is when we go left to right, if I'm following the top arrow, that is photosynthesis. You know photosynthesis is going to occur in chloroplasts. You already learned that. The new part is who's going to be, if we're moving electrons around, who is our mule to carry our electrons? And that's going to be who? NADP. He is our mule. Okay? And we remember NADP, we can think plants or photosynthesis, though the P stands for phosphate, but it works. Okay. And in that process, making sugars, that would be an anabolic reaction overall, right? So if I'm making sugars in an anabolic reaction, I need to have energy on the reactant side because it's requiring energy. That energy is going to come from where? The sun, right? And I'm going to reduce the CO2 into glucose, and I'm going to oxidize the water in just a plain old oxygen, okay? That is what you're doing in photosynthesis. The reverse of that occurs in cellular respiration, which we're going to start learning about tomorrow. You're going to start burning this fuel, burning sugar, just like a combustion engine burns gasoline, okay? You're going to burn this sugar, this potential energy, and as you oxidize the glucose into CO2, you're going to release some energy, which you're going to use to build what? ATP. Okay. And also, you're going to, in order to make that work, oxygen is going to have to be reduced. And remember how in the electron transport chain, in that example, for oxidative phosphorylation, which you'll learn later, oxygen had to be at the bottom. Remember, to take the electrons so we could keep our chain moving so we could make that ATP. Okay, how do you feel about this one? Oh, and our mule, it happens in the mitochondria, and our mule is NAD. Okay, anything you want to ask me about that slide? Okay, and then this one, Hi. Dun, 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 dun. Here it comes. Do you guys see my mouse anywhere? Oh, right there. Thank you. I'm trying to get it over onto this window. Okay, this one right here was giving you the example of an electron transport chain. Okay. Okay, giving you an example of an electron transport chain. And so you're passing those electrons along, and when you pass those electrons along, is it 100% transfer? No. So you're going to use some of the energy, though, in the transfer to pump hydrogen ions to one side of a membrane. And we know we can use that because when it comes back in, we can make some ATP from that. All right, you okay with that part? Okay, and then that is the very end. And do you have any questions you want to ask me? Yes.
Yeah, so if the first electron that enters, if you'll lose them as heat every time,
Yes.
couldn't you lose it as like sound or light, not always heat?
Sure. Like when you give off a color when an electron comes down. Sure. Yes.
Okay. So that law is like kind of.
No, it's good. You lose energy. I just gave an example as heat. Yeah. Any other questions that you have? Are you glad you came? Okay, good. I love you. Make good choices. You will survive the week. The obstacle is the way. Go through it. That is the way you must travel. I'm already proud of you. And let me see if I can turn this off correctly.